Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the next class of this course. So we have been working on the kinetic theory of gases, and maybe we will quickly recap what we did in the last class. Okay. So basically we are working on this kinetic theory where we are working with what is known as ideal gases under all the assumptions that gas molecules are not interacting with each other. The only source of energy that they have is the kinetic energy. The molecules are point like, they do not so they have elastic collisions, right. So under those simple assumptions, approximations, it turns out there are some easy quantities that we can calculate, and one of the thing that we did in the last class was pressure exerted by an ideal gas, right. So pressure by an ideal gas, and we saw that the expression for the pressure is 1 by 3 m times n divided by capital V times V squared average, right. So where m is the mass of single molecule, n is the total number of molecules in the container whose volume is capital V, and V squared is the mean squared velocity. So this is the pressure, right. And later we also defined another quantity which is known as temperature. So we defined temperature in such a way that the average kinetic energy of the gas molecule is equal to 3 by 2 times kBT, where kB is the Boltzmann constant. kB is Boltzmann constant. Right, and the temperature is nothing but just the measure of average kinetic energy of the gas molecule. All right. So therefore, if we substitute this back there, so we get this very important equation which is n kBT, and this is nothing but the ideal gas equation. Okay. And also from here we defined what is known as root mean squared velocity, which is equal to the square root of average of mean squared velocity, and this is given by 3 kBT divided by m. All right. And in the last class we basically estimated the velocities of these gases for typical gases like carbon dioxide, nitrogen, argon, and so on, right. Okay. So remember when we say it is a root mean squared, right. So we use the term mean, which means it's an average velocity. It's not that all the molecules are moving with this velocity all the times. This velocity is averaged over all the molecules in the room, right. So in some sense, some way of thinking about is like if I take a snapshot and at that particular moment all the molecules are moving with different velocities, right. And also in the last class we in order to calculate the pressure exerted by this gas, we divided the gas molecules into various subgroups between 1, 2, 3 so on up to G, and we assigned certain velocity to certain group, right. So we kind of assumed that there is a well defined underlying distribution of molecular speeds, and in this class this is exactly what we are going to evaluate, right. Okay, so for today's class, so what we will do is distribution of molecular velocities for an ideal gas, right. Okay. So, again we will make some assumptions, right. So, assumptions. So, the first assumption is that the gas is at thermal equilibrium. Right, and we discussed about thermal equilibrium, right. So, if the temperature of the gas is not changing as a function of time, then which means its average kinetic energy is not changing, right, per molecule is not changing, or the Vrms is constant. So, we can write here Vrms does not change with time, In such a situation, we are in equilibrium, right. So, we are getting this equilibrium distribution of molecular velocities. Okay. The other assumption is molecules are moving randomly in all directions. Okay. So, in space x, y and z axis they are all alike, right. So, there is no preferred direction in which molecules want to move. Okay. And the third assumption is so molecules move translationally, whereas which means no rotational or vibrational modes, right. So, what do we mean by that? So, that means the contribution to the kinetic energy comes only from the translation, right. So, the molecules are only moving in space, there is no internal degrees of freedom in the molecule, they are not really rotating or vibrating. So, we are ignoring all that, all right. So, this is another important assumption, and this is true if we are assuming these molecules to be spheres, right, sphere like molecules. So, I will come back to a more formal definition of degrees of freedom when we discuss the topic of statistical physics in this course as we go along. And remember what we are interested in. So, our goal is to basically find number of gas molecules moving between certain velocity interval, say v, let me use this symbol v and v plus dv. Okay. So, this is our goal, and let us call that number to be d and v. Okay. So, let us use that notation. Okay. So, this is our goal. So, we want to, so in this room I just want to see how many molecules are there between certain velocity v and v plus dv, what is that number. Okay. So, this is what we are interested in. Okay. So, let us see how we can start, right. So, again I would like you to imagine that that you have a 3-dimensional space, right. So, we have say x, y and z, and we have these gas molecules, right, moving everywhere. So, these are gas molecules and they are moving with certain velocity, where the arrows represent the direction of velocity and the length of the arrow is its magnitude, and there is certain distribution, right, which is unknown to us right now. Okay. So, these molecules are moving with certain velocity in certain direction, right. So, what we can do is we can move all these vectors to a common origin point, right. So, basically move all these molecules to a common origin point and just look at the velocity vectors, right. So, since they are random in all directions, so you just get many such vectors pointing radially outwards, something like that, right. Where again and this is a sphere, right. So, this is a 3-dimensional, so this is a spherical structure, right, and the velocity vectors are coming radially outwards. Okay. and therefore, it is now convenient for us to move into the velocity space. Okay, so let me do that. So, say you have, so let us say this is Vz, this is Vy, this is Vx, right, and say there is a point in space, which is which has coordinates. So let me, so this point P, right, and P is Vx, Vy, Vz. So certain x, y and z components of the velocity, and what we can, since we are interested in the number of molecules between V to V plus dV, right. So basically, so molecules or number of between V and V plus dV, right, and remember these are vectors, and V we can just write as Vx, Vy, Vz, right, and V plus dV is just equal to Vx plus dVx, Vy plus dVy and Vz plus dVz, right. So, this is what we have, these are the corresponding components, and how would that look like? So, that looks like certain volume element in this velocity space, right, which looks something like this, right, where this axis, I mean this side is dVy, this side is dVx, and this vertical is dVz, right. And we are interested in how many molecules are there in this volume element, right. So, that is what we are interested in. Okay. So, how do we do it? So, let us do it step by step. So say total number of gas molecules is capital N, all right. And say so if delta Nx is number of molecules with velocity between Vx and Vx plus dVx, then the probability to find a molecule which lies between the velocity Vx and the x component of velocity Vx and Vx plus dVx. So, that would be given as Px, which is nothing but those number of molecules divided by total number of molecules, and let us write it in form of f of Vx dVx, right. And what is f of Vx? So, f of Vx is the probability density function, right. And what is Px? So, the probability. Okay. So, probability of finding a gas molecule with its x component of velocity lying between Vx and Vx plus dVx. And this probability density function has dimensions of inverse velocity. So, remember probability is a dimensionless quantity. So, dVx has dimensions of velocity. So, f of Vx has to have dimensions of inverse velocity. Okay. So, similarly, we can write similar equations for y and z component. So, P of y will be delta Ny divided by capital N, and that can be written as f of Vy dVy, and P of z is delta Nz divided by N, which is f of Vz dVz. Okay. So, these are three individual probabilities for velocities of gas molecules to lie between Vx and Vx plus dVx, Vy and Vy plus dVy, and Vz and Vz plus dVz independently, right. But what we are interested in is, we are interested in the joint probability, right. So, we want same molecule to have its velocity component between the Vx and between dVx, dVy and dVz at certain Vx, Vy and Vz, right. So, therefore, what will be the joint probability? Therefore, joint probability Okay. So, joint probability will be Px times Py times Pz, right, product of 3 probabilities, and that becomes f of Vx, f of Vy, f of Vz, dVx, dVy, dVz, right. And what is, again, what is probability, right? So, probability is basically number of these molecules lying in this volume element divided by the total number, right. So, this I can just write as so the notation that I used, which was d of nv. So, let us use that. So, d of nv divided by n is exactly equal to Px times Py times Pz, and this is f of Vx, f of Vy, f of Vz, dVx, dVy, dVz. Okay. And we can also define the density of these gas molecules in the velocity space, right. And what will be the density? That will be the total number of molecules divided by the volume element. Okay. So, basically the density would be so d, and so let us call that rho. So, okay. So, define density in velocity space. So, density in velocity space to be rho, which is dnv by dvx, dvy, dvz, right, because that is what the volume of this this element is. This is dvy, dvx times dvy times dvz, right, and that simply becomes n times f of Vx, f of Vy, f of Vz. Okay. All right. So this is what we are interested in. So, but remember, for that we have to evaluate what is f of Vx, what is f of Vy, and what is f of Vz. Okay. So, that is what we have to do. Okay. Okay. So, remember, since we made the assumption that molecules are moving randomly, right. So, there is no x, there is no preferential direction in which they are moving. So, as long as the magnitude of the velocity, okay, so what is the magnitude of the velocity in terms of Vx? So, magnitude of velocity, which is V, this is nothing but square root of Vx squared plus Vy squared plus Vz squared, right, or we can just write it as this: V squared equals Vx squared plus Vy squared plus Vz squared. Okay. So, as long as this velocity magnitude is constant, all the combinations of Vx, Vy and Vz, which give you the total velocity of V, so this density should not be function of that, right. So, it has a radial, it has a symmetry associated with it, right. So, therefore, this rho, which is a function of Vx, Vy, Vz, as long as those Vx, Vy, Vz satisfy this equation, it should be independent of V, right. So, therefore, d of rho by dV equal to 0, because we assume velocity space to be isotropic, okay. And if we basically evaluate this differential, so this basically just becomes d by dV of n times f of Vx, f of Vy, f of Vz, and that should be equal to 0, and this can simply be written as using the chain rule of calculus. So, this is del by del Vx, so del by del Vx of n times, so n we can actually write outside. Okay. So, since we are equating it to 0, we can conveniently remove n from this equation. So, let me just get rid of it. So, del del by del Vx of f of Vx, f of Vy, f of Vz times dvx by dv plus del by del Vy of f of Vx, f of Vy, f of Vz, and same thing for the z. Right. And we can move this common dv factor to the right side and multiply it by 0, and we are finally and okay. So and okay. So let's okay. Well, the other thing is, so let's divide this equation. So divide both sides with fx, f of Vx times f of Vy times f of Vz, right, and get rid of this dv term. So we have, therefore we get 1 by fx, okay. So so 1 by f of Vx times del f of Vx by del Vx times dvx plus same terms for y and z. Okay. So this is what we get, and let us call this equation number 1. All right. So this is the equation which has quantities like f of Vx, f of Vy, and f of Vz, which we are interested in. So that is one equation. But remember, we have another equation, right. So we are assuming that these Vx, Vy, Vz they have to satisfy this condition, right. So from this equation, for any constant v, right. So for a constant v, right, the so this terms become constant, and if we take derivative of this, the derivative of this right hand side should be 0, right. So for a constant v, we can modify, we can just take derivative of this equation and we get this condition. So basically Vx dvx plus Vy dvy plus Vz dvz is also equal to 0, and let us call this equation number 2, right. So now we have two equations. So this is the primary equation that contains the quantities f of Vx, y and z, and there is another equation which puts certain constraints on these quantities, right. So these variables dvx, dvy, dvz, they are related to each other using this equation, and this is a typical mathematical tool that we use in order to calculate such equations, and one method to do that is called method of Lagrange multipliers, right. So in which what we do is we take the primary equation, right. So like so which is equation 1, multiply that by an undetermined parameter, unknown parameter, a constant which we are calling it 2b, right, and multiply that with equation 2 and equate it to 0, okay. And this is known as method of Lagrange multipliers. And here 2b is a Lagrange multiplier. Okay, this is a mathematical tool in order to solve these equations. Okay. Now if we do that, so what we get is, okay, let me write it. So we have 1 by f of Vx del f of Vx by del Vx dvx plus 1 by del f plus 2b times the constraint equation and this is equal to 0. Okay, so this is what we have. Alright, and now what we will do is we will just combine. So, remember variables here are dvx, dvy, dvz, right. So, we will just rewrite this equation as follows: 1 by f of vx del f of vx by del vx plus 2b vx times dvx plus same term for y, right. So, all you do is you just replace x with y times dvy plus same z term, which I am not writing, dvz, and that is equal to 0. Okay. So, now that is what we have, so that is what we end up with, right. Okay. So, now how do we do it, right. So, the step 1 is that what we do is we choose the Lagrange multiplier value, we choose b or 2b such that the quantity in parentheses here just becomes 0, okay, such that 1 by f of vx del f of vx by del vx plus 2b vx is 0. Okay, that is the first thing that we do, and if that becomes 0, so we are just we are left with only these two terms, right. So, let me write that. So, therefore, we are left with so we are left with 1 by f of vy del f of vy by del vy plus 2b vy times dvy plus 1 by f of vz del f of vz okay. So, this is what we are left with. So, if we if we set this term equal to 0, so this equation just reduces to this. Okay. But remember how many variables we have, right. So, we have dvx, dvy and dvz, right. So, there are 3 variables in the problem, but they are related to each other by this constraint equation, right. So, therefore, the total number of independent variables that we have is not 3, but 3 minus 1, which is 2, right. So, there are only 2 independent variables here, and let us assume that those 2 independent variables which we have complete freedom, they are dvy and dvz, right, which means that these dvy and dvz can take arbitrary values, right. So, there is no bound on this. So, therefore, for this equation to be true, both these quantities in the parentheses have to be 0, right, both of them have to be 0 at the same time, right. So, maybe I can write a little bit. So, so since dvx, dvy, dvz variables are related through through equation 2, right, through equation 2. So, we have 2 independent variables. And let us assume those are dvy and dvz, and in order for this equation to be true, these quantities in the parentheses have also to be 0, right. So, therefore, so 1 by f of vy del f of vy by del vy plus 2b vy is also 0, and 1 divided by f of vz del f of vz by del vz plus 2b vz is also 0. Okay. So, therefore, we have 3 equations, this equation maybe. So, we have this equation, this equation, this equation, which now can be solved for Vx, Vy and Vz, right. So, let us just solve one of them. Okay. So, let us start with let's start with this first equation and let's rewrite it in a different way. So, so we have to solve these equation, right. So, solve x equation first, x equation, right. So, we can rewrite that equation as follows. So, I am rewriting this equation as follows. So, this is d of f of Vx by f of Vx equals minus 2bVx dVx, right. And what I have done is I have just replaced these partial derivatives with the full derivatives because this f is only function of Vx. So, so both mean the same thing, right. And this is like a straightforward integral to solve. So, we get log of f of Vx equals minus b Vx squared plus log a, where log a is a constant of integration, right. Integration. All right. And so, this becomes so f of Vx equals a times exponential of minus b Vx squared, right. So, this is how it can be written. So, similarly the solution for Vy and Vz is identical. So, similarly f of Vy is also a e raised to the power minus b Vy squared, and f of Vz is equal to a e raised to the power minus b Vz squared. Okay. And in fact, I have used the same constants of integration because there is space is isotropic, right. So, there is absolutely no difference between Vx, Vy and Vz. Okay. So, therefore, the constants of integrations are also equal to a for all these three equations. Okay. So, yeah, so this is the final the things which we were interested in, these the distributions of x, y and z, the probability density functions, and now we will basically just plug this back into in here, right. So, what is the so we can just write down the density in velocity space. Okay. So, therefore, so maybe on the next page. So, therefore, rho, which was nothing but n times f of Vx, f of Vy, f of Vz, that simply becomes n a cube exponential of minus b Vx squared plus Vy squared plus Vz squared, and this is n a cube e raised to the power minus bv squared, right. So, this is our rho. So, this is the density of these gas molecules in the volume space. And I will just maybe quickly draw this, how this, and remember this is a function of v, right. So, there is v here. So, rho is a function of v. So, let me write it like this, rho is a function of v, and we can like see how it looks like, how the plot of rho looks like as a function of v. So, your x axis is v, y axis is rho of v. So, you can see that if v is 0, this quantity becomes 1. So, you start with a number which is n a cubed, right, and then it then as and remember this is v equal to 0, I can mention that. So, this is 0, and as you start increasing v, so this exponentially decays, right, and there is a and this function has a name, this is known as Gaussian function or normal function, right. So, therefore, the number density of these gas molecules in the volume space maximizes at v equals to 0, right. So, this is the first result that we got, but remember we are not interested in the density, we are interested in how many number of molecules are there in the volume element, right. So, basically what we have to do is we have to evaluate okay. So, So, what rho is? Rho is just the density of these molecules in this volume space, in this velocity element of this volume element in the velocity space, but we are interested in total number of such molecules. So, that will be the density times the volume of this element, right. So, we are basically interested in, so the quantity d and v which is rho times dvx, dvy, dvz. Okay. So, that is what we called it here. So, d and v which is n times rho times dvx, dvy and dvz. Okay. So, okay. So, now since okay, so remember we moved all these velocity vectors here. So, since and there is a spherical symmetry in the problem. So, this integral is much easier to do in a spherical coordinates, right. So, we will convert this volume element in Cartesian coordinates into the spherical coordinate system, and in spherical coordinates this just becomes okay. So, in spherical coordinates, so our dvx, dvy, dvz just become v squared sin theta, d theta, d phi and dv, okay, where v is the radial direction, right. So, v so where v is radial coordinate, okay, phi is the azimuthal and theta is the polar angle, polar coordinate, okay. And our v basically goes from 0 to v, phi, so phi goes from 0 to pi, and theta goes from 0 to 2 pi. So, if we put it back there, okay, so therefore, we get d of nv is equal to theta going from 0 to pi, phi going from 0 to 2 pi, sorry. So, here the theta goes from 0 to pi and phi goes from 0 to 2 pi. Okay. Times n a cubed, right. I am just putting these values here, e raised to the power minus b v squared times v squared sin theta, d theta, d phi, dv. Okay. So, here we can see that the integral of d phi will just give us 2 pi, and the integration of sin theta is minus cosine theta, which we have to evaluate between limits theta equals 0 to theta equals pi, right. So, let us do that. So, therefore, d n v becomes n a cubed v squared e raised to the power minus b v squared times 2 pi, right, that is the phi integral, times the integration of sin theta, which is minus cosine theta evaluated from 0 to pi, right. And what is that? That is basically minus 2 times minus, so that becomes 2, right. So, we get finally we get 4 pi n a cubed v squared e raised to the power minus b v squared, there is a dv here, dv, right. So, d of n v, okay, or we can define a term f of v, which is d of n v divided by dv, this is equal to 4 pi n a cube v square e raised to the power minus b v squared, and this is the final result that we were after, right. Okay. So, this gives us the probability, the number of molecules lying between, okay. So, dNV tells you the number of molecules in the volume element of size dV at velocity value v, right. So, let us look how, let us try to see how it looks like, right. So, let us plot this quantity f of v as a function of v, okay. So, see, like it's so it is a function, it is a product of two functions. The first function is v squared and other function is e raised to the power minus bv squared. So, when v is very small, the contribution will come from the first function, which is v squared, and it is nothing but a parabola. So, let me draw a parabola. So, this is like how it will rise, but maybe, okay. So, this is the v squared contribution, but as we keep on increasing v, so again this is 0, this is 0. So, as we keep on increasing v, the other function will take over and it will drop down, right. So, here the contribution comes from v squared and here the contribution comes from minus bv squared, right. So, this is how typically this distribution looks like, and the advantage of this is that so if I just draw a tiny window of dV at certain velocity v, right, at certain velocity v. So, if I just evaluate the area of this strip, that will tell me how many number of gas molecules are moving between the velocities v and v plus dV, okay. So, this is the advantage of this expression, and it has a special name. It is called Maxwellian distribution of molecular speeds. Okay. So, this is what we were interested in. But remember, our job is only half done because we do not know what the values of A and B are. So, B was some arbitrary constant Lagrange multiplier and A was the constant of integration. Okay. So, how do we evaluate that? Okay. So, basically evaluation of unknown constants. A and B, okay, that is our next job, that is our next aim. Okay. So, we will basically use two properties. The first one being, if I calculate the total area under this curve, what would that be? That will be the total number of gas molecules, right. So, what do I mean by that? So, if I evaluate this integral of d and v, right, between velocity 0 to infinity, that would be just n, which is total number of gas molecules, total number of molecules. Okay. So, that is what we will do. So, we will just plug this d of nv here. Okay. So, this just simply becomes 0 to infinity 4 pi n a cubed e raised to the power minus so times v squared e raised to the power minus bv squared dv, and this we know is equal to n, and I will just rewrite this in this way. So, I will take out these constant terms outside, 4 pi n a cubed 0 to v 0 to infinity, because velocities can be infinite in theory. So, this is v squared e raised to the power minus bv squared dv, and this is n. Okay. Now, we have to evaluate this integral, right, and again from mathematical physics course, this is a well known integral. In fact, there is special class of this integral which is known as gamma function. Okay. So, gamma function which basically tell us any integral, general integral between 0 to infinity of b raised to e raised to the power minus b v squared times v raised to the power n dv is equal to 1 by 2 b raised to the power n plus 1 by 2 times a gamma function, this is capital gamma, times n plus 1 by 2, and the value of this integral is known for various n values. So, maybe I can tabulate it here. So, say this is your n, okay, and this is your gamma of n, right. So, if your n is half, the value is square root of pi. If your n is 1, the value is 1. If your n is 3 by 2, the value is square root of pi by 2, and so on. The value is 3 square root of pi 4, and so on, okay, and so on. Okay. And here you can see that the n is basically sorry, I missed one. So, after 3 by 2 we should have 2, okay, because in our case n is 2. So, if n is 2, your gamma of n is again 1, and if this is, so if this is 5 by 2, the value is 3 square root of pi by 4, okay. And you can see in our case n is 2, right, because we have v squared, right. So, n is 2. So, therefore, what we will do is, okay, so in our case n equals 2, which implies we have to use the gamma, which is 3 by 2, and this is nothing but square root of pi by 2, right. So, if we plug that into here, so what we eventually get is 4 pi n a cubed times 1 by 2 b raised to the power 3 by 2 times gamma 3 by 2, and that is equal to n. And if you just use gamma 3 by 2 as square root of pi by 2 and you do little bit of algebra here, so you will get a cube equals b by pi raised to the power 3 by 2, or you can write your a as square root of b by pi, okay. So, we have a in terms of b. So, that is the first relation that we have. Now, we will use another property, right. So, from this distribution we can calculate the mean squared velocity, right. So, let us do that. So, the mean squared velocity from the distribution by definition would be 0 to infinity v squared dnv divided by 0 to infinity dnv, right. And we will again substitute all these value of dnv, expression of dnv here, and we will cancel out all the constant factors which are in both numerator and denominator, and we get 0 to infinity v4 e raised to the power minus bv squared dv divided by 0 to infinity v squared e raised to the power minus bv squared dv. And again you have to just see what gamma functions do these integrals correspond to, and if you check that, it becomes basically 2b raised to the power 5 by 2 gamma function of 5 by 2 divided by 1 by 2b raised to the power 3 by 2 gamma 3 by 2, and if you substitute these gamma values here from here, so we will just get this is basically 1 by b times 3 by 4 square root of pi times 2, and this is nothing but 3 by 2b, right, and this is our v squared average, right. So, but remember from kinetic interpretation of temperature, our v squared average is nothing but 3 kBT divided by m, and we will equate that with this number which gives us the value of b as m by 2 kBT, okay. So, that is our first, that is the Lagrange multiplier that we had, and if you substitute your b value here, so you can write down your a to b. So, just put b here and you get a equals square root of m divided by 2 pi kBT, okay. So, now we know our unknown constants a and b. Now we will basically plug that back into the expression of Fv. So, therefore, our Fv takes the final form which is 4 pi times n times m by 2 pi kBt raised to the power 3 by 2 times v squared and exponential of minus mv squared divided by 2 kBt, and this is the final Maxwell distribution. This is the final expression of Maxwell distribution. So, we can end our class here. So, in the next class we will just try to understand what does this distribution signify. So, remember it is a function of temperature, right. So, we will qualitatively try to get a feel like how this changes with temperature, and yeah. So, see you in the next class.